Okay, so thank you, everybody. I'm pleased to talk, as you see, on split processes, bringing the process to a data. I'll just say that I have to go teach after this. I'll be back in the evening and tomorrow, but also two of my PhD students have worked on this project and can also answer any questions. So one right up here is Yao Shu. Just stand up, Yao. And then second back there we have Twinkle James. Thank you. So the idea is this. In fact, I've been working a lot lately in high-performance computing as opposed to cloud and data storage. But of course, this is a talk that's joint with Peter and Oren, who have the expertise in the data storage in the cloud. And I think at this point we have something that has been proven in near production, which can be quite useful also for the cloud and data. So the idea is process migration has been a dream for people for a long time. In a sense, we have it right now if you use a virtual machine or if you use a container. On the other hand, if you want to do it directly on essentially bare metal, the host, that hasn't been easily available, and here it is. And that's nice because otherwise you have to worry about the plumbing between the virtual machine or container and the actual host. So here we can do it directly with no compromises. So as I said, the motivation here is going to be bringing the process to the data. So imagine in the cloud you have processes which need to access various data stores, and they may need to take many hops. There can be quite a lot of inefficiency there. So if we can remigrate all your processes so they're closer to where they need to be, then you're better off. So this is the idea. So we want to be able to do this dynamically in the middle of production, to stop and reorganize where your processes are being hosted. The advantages here are that you don't need any configuration files in advance, and furthermore, you can just do dynamic realignment. So let's talk first a little about the background. So here first, just a very brief introduction to MPI. MPI is the de facto language behind parallel computing on large clusters. MPI more or less falls into two families of calls. Point-to-point, the classic send a message, receive a message, probe, is there a message waiting for me? And collective communication, classic barrier broadcast, many-to-one communication, one-to-many, and so on. So, in particular, one of the features of MPI, so this is the motivation which I'll then bring back to the cloud, I haven't forgotten, is the idea of what they call a Cartesian communicator. So often in your scientific simulation, you want to have a Cartesian grid right there on the right-hand side. And each node will represent either one of those grid points or maybe a collection. And now the problem is that in the simulation, we know what nearest neighbors look like, but this is unlikely to match what you have down in the hardware. In the hardware, very often you have some kind of, for example, toroidal topology with a weird interconnect. So this idea of creating in software a Cartesian grid is fine, but then it's not going to map well onto the hardware. And so this is where vendors right now tend to provide a utility in which they try to measure the performance and how many hops are needed. And then in a dry run, and we can see that here, and then in this dry run, they will try to figure out, take statistics and then they will run the jobs one more time, hopefully placing each process where it should be from the very beginning. So there are problems with that. One problem, of course, is you need the configuration files for the dry run. Another big problem is you cannot change it dynamically. So if your mode of usage changes over time, then you're stuck. So in green, we have the workaround where you would use a configuration file. In red, we see what the problem is, that we want to dynamically reorganize the technology. So now we come to the solution that was developed in the space of high-performance computing. And then I'll just say a few words again about why this should be relevant to processes in the cloud and bringing the process closer to the data store. Again, recall that this is executing essentially on bare metal on the direct host. So we don't have any of the possible inefficiencies because of plumbing going to a virtual machine or a container. In particular, this technology works also with standard accelerators such as GPUs. So my student Twinkle Jane had presented at SC how to extend the techniques I'm describing here to also work well with GPUs. So in any case, VMTCP has a long history. It's been around for about 15 years. It should be easy to use, standard commands, launch, checkpoint, restart. A bunch of publications by now of other groups using our software. So it has a track record. And here's the basic idea. Here's what split processes are. I'm going to show you this essentially 3 times just to make sure that I really hit it home. Because this is a technique that was developed quite recently. The original technique was published in 2019, and now we have an improved version that's still more performance. Furthermore, we have a 3-way collaboration going in which this is going to be in which this is now in near production with the NERSC Supercomputing Center, where they host the #8 supercomputer in the world, and a startup company called Membridge. So the key idea is that we can load 2 programs into a single process, single address space, single thread. And from the viewpoint of the operating system, there is only one process, one thread. That's the whole story. But in fact, we have an upper half program and a lower half program. Each will have its own libc library and so on. They don't interfere. They can each execute independently. Except here's the game that we're going to play. The upper half program is whatever your application is. Presumably your application is following some nice is going to make calls to some nice library. In our example, it's MPI, but it can be whatever library that you happen to have chosen as a convenience library to access the environment. So at that point, we will call the lower half. In this case, we will be making calls to the MPI library. So at the time of launch, the upper half will have wrapper functions, which binds in the lower half. It turns out to be extremely efficient. And then, when it's time to checkpoint, the secret is that we have tagged all of memory so that memory is either part of the upper half or the lower half. And now, we'll save only the upper half of memory, the memory associated with the application. And we're going to throw away the lower half. We'll throw away the system libraries. We don't need them. And that's good, because they're very closely tied to the hardware, and we don't know how to save hardware. Saving hardware or restoring hardware can be a very difficult operation. So at that point, we can then go to restart. And then when we restart, we'll just bring in a new, fresh lower half that we will then restore the upper half memory. And this upper half memory will then rebind its calls to the lower half MPI library. And now everything works fine. And all of this is based on top of our VMTCP checkpointing project that's been around for 15 years with a number of users, including, for example, Intel Corporation. Okay, and then here's another Oh, please. Good.
All right, so so I just wanted to add that, to extend this, that so Gene has done, I've collaborated with Gene on a number of things, and here he has something which has been done in the high performance computing world, but we want to also be able to use these techniques in the cloud. And really what's being, what can be done here is, the whole principle of moving compute closer to data is do it everywhere, from NUMA to virtual machine migration. Now, there's various ways that you may want to migrate things, and migrating a process actually is hard. Migrating a virtual machine, yes, but then you have to package everything up, provide the address, move that, networking requirements and that other things. So what's intriguing about this is the split process mechanism. It was developed for a specific checkpointing application for batch computing. Gives us this general mechanism to cut the the strings that are binding the process to the local machine, and then reinitialize those after we migrated it somewhere else. We should be able to migrate in and out of containers and do a number of other things, and essentially allowing near data processing, letting us transparently migrate the processing to close to cached data, for instance, or to where it's actually being cached. So that's the extension on the, for my, non-HPC side work of what we wanted to do with this technology. So I'll let Gene finish this up.
Thank you. And as I promised, I in fact have 3 slides on this topic. I figure if I say it 3 times, maybe you'll believe that it works. So all 3 really are saying the same thing, but it actually has been proved in production, believe me, we have enough more stories to know the difference between an academic prototype and a production version. So here's another way of saying exactly the same thing. We have the upper half program, and we will bind any calls to the lower half, and there you can see the arrow showing the binding. You can see 2 link maps. These are the maps which include all of the libraries that have been linked in. There will in fact be 2 copies of libc, but otherwise in the lower half you've got those special system libraries that are so annoying because they're so closely tied to the hardware. But we can restart and just grab a fresh lower half. And this is a quick review of saying the same thing. So if later you want to review this, you can look at the slides, and hopefully this text version will remind you of what are the essential points behind those diagrams. So as I said, it's a 3-way collaboration. The MTCP is the underlying checkpoint project. MANA is the version for MPI that includes the idea of split processes. And it's a 3-way collaboration. There we see NERSC and Merge, and quite a few people who have collaborated with us, both from my group and from the other 2 organizations. So I think that more or less concludes the main idea, and as Peter has already summarized exactly why this is so intriguing for the cloud. Are there any questions? Thank you. Oh, I didn't see it. Please.
I worked on EPROM many years ago, because it's a matter of how the process migration that you talked about when it works. I know that there are a lot of issues at the memory. I know there's a lot of issues at the memory dumping level. Could you talk a little bit about that split? And I'm thinking applying what I know there to a generic cloud workload. Go back to the slide right there. So if I have a linear algebra library, so it's doing a lot of math and a lot of hardware level stuff, is that going to be the lower half or the top half? And if it's in the top half of the migratable part, how do you deal with the memory mapping of that? And what do I have to do to get some other application to work the same way?
So you will choose at what API you want to use to split between the upper and lower half. You can put the linear algebra library in the lower half, or maybe you'll put it in the upper half and put some system libraries only in the lower half. You make the choice, and that determines where you place your wrapper functions that'll have to bind things. And I think that I wasn't supposed to go too much on questions.
Yeah.
Oh, okay.
Actually, I think there the library, that library should be up in the upper half. I mean, there's the preserving the memory mappings that has in fact been, a key part of the checkpoint and presumed, work for quite a while. Now, how it interacts with ASLR and some other things like that, honestly, I need to talk to Gene more about that. We haven't actually discussed that. So,
Yeah, the ASLR is not a problem. We've seen that.
Great. Okay.
It doesn't.
Great to hear.
Yeah, and similarly, in the case of MPI, we chose the MPI API as the interface in which we want to split. In principle, we could have chosen the lower level network library as the API. We do have that flexibility. We can do it either way. Other questions?
I will remind industry participants that you can fill out the Airtable entry, and if you don't have a link to it, you could email T Moran, TMORAN @edu.edu. My apologies, Tara. Then she should be able to get you a link. Hopefully everyone has a link, so you'll get those emails. Any further questions? All right, we'll give you another minute to give any updates while we're getting our next talk queued up.